Thanks for the introduction. Well, thanks very much all for coming along. I'm the David Cox. This is my nephew Graeme. I'm a farmer in Australia. Was a John Deere dealer in about 4 or 5 years in the 1980s. All my family were cattle people, and I was the youngest of 6 kids, and I wanted to be a farmer. And started on so I had to transform grazing land into farming land, and it was that point in time where laser technology just became available, and so I found it in the US at Tulare Farm Show, and I took it back to Australia and became the importer for laser plane products for my state back in 1979. I'll say I was extremely impressed with the gentleman that designed laser, the Mr. Studebaker that came up with the laser concept. I've always been in awe of his vision. For a fellow to take a medical laser, put it on an axis, spin it round, and guide the roughest, toughest farming equipment was really, he had some vision. I never met him, I met his son, but Mr. Studebaker died before I could get to meet him. But after, I've been, as a farmer, I've driven bulldozers clearing the land. I drive laser pans, what we call laser buckets, laser scoops. I've driven them myself. And after getting over the euphoria of how good laser is, you start to criticise and you start to come up with the shortcomings of laser. Now the basics are the world's soil surface isn't a straight line like a laser beam is. The reality is it's either slightly convex or concave slopes. I might be following the script here.
You kill the lights. Yeah, you killed the script already.
I jumped the script back. I'll follow the script now on my nephew's request.
You going to take it through what we're going to tell them?
Okay, I'm going to do the first one. Just where it started, what was the catalyst for the development of this product. Then Graeme will take over and do, I'll do some of the concept in part of this story, but then Graeme will take over and do these. We're on pretty flat country, just like you here, and our average grade was about 0.05%. We had flatter country than that and steeper country than that, but about 0.05 is the average. And you've got to have good levelling to get drainage on 0.05, so that after a rainfall event there isn't pools of water left. I'll say I was born at just the right time, I believe. Our country, we would have struggled to have developed it with grade stakes. It's pretty poor soil, powdery topsoil, and lots of dust while you're landforming. And to go out there and attempt to put grade stakes in and not end up with the grade stakes staking the tyres is the first thing that happens, and then knocking them over in the dust because you can't see where you're going. There wasn't going to be a lot of our land developed with dumpy and grade stakes. But just at the right time, lasers came in for me, and as I say, I was extremely pleased with the laser concept. But then we needed to be able to change the grade. Okay, we know with the varying slopes on the farm, we did need to change the grades to try and lessen the amount of earth shift. I will acknowledge we weren't growing rice, so we didn't have the constraints of having to put levee banks up. But this field here is an actual field of mine. And that was a multiplane design using Trimble software. And in my opinion, that was designed by the best multiplane designer in the world. He lives in our district, and he's the only one that I know of that will spend 15 to 20 hours doing a design like that. These little intricacies here of tight little corners just to get the sections to butt together without a lip. It's a painstaking operation. So that, after I did that a few times, I said there must be something better. This is the shot of our irrigation. Our furrows, I try and make them all 1 kilometre long. That's 5/8 of a mile. We're all sugarcane. I would have liked this shot to have gone out a bit further. I'm what we call a controlled traffic fanatic. In row cropping, there's 2 ways of reducing compaction. One's by putting great big tyres on to increase the surface contact with the ground so you have less pressure per square inch, but over a much bigger area. The other concept that's increasingly coming in is what we call controlled traffic, where we put very narrow tyres or rubber belts onto zones with GPS guidance, and we compact those little traffic zones. Mine are 20 inches wide. I currently grow cane at 1.5 metre centres, but all my equipment that goes into the field has the wheels 3 metres apart, just a bit under 10 feet. And so that's a traffic zone. This furrow is a non-traffic zone. That's a traffic zone, non-traffic, then the harvester jumps into the traffic, misses one and goes into traffic. So we're compacting, in our situation, about theoretically 16% of the soil surface. In the world sugar industry, that's a record. No one else achieves that. Because with the laser levelling, we do remove topsoil, varying amounts of topsoil. In our soil type, there's very shallow soils. It's fairly good top 6 or 8 inches, but pretty poor under that. And so it's pretty important for us not to shift topsoil. Here we have, and the result, if you go to our laser design, that's where the cut is, that's where the cut is, that's where the cut is. Actually, this one over here, I'll just let you know, wasn't cut. It was just a natural, extremely poor soil right to the top. But all these other red and orange areas were cuts. And so after we'd done the damage to that soil, I was looking to remediate the soil with lime and gypsum. And before, up until this point, I would have probably put a bag to decide where I put my lime and gypsum. I would have put a bottle here and a bottle over here and drawn a straight line between those two, and just put 3 tonnes per acre on this, and about 6 or 8 tonnes per acre on all this area here. But when you have a look at the histogram here of how much bad soil there is and where the good is, there's not a real lot of bad areas. So instead of putting those average amounts of soil conditioners on the whole block, we now target the biggest amount on these red zones, and we'll, I talk in tonnes per hectare, we put about 14 tonnes per hectare, something around 6, 7, 8 tonnes per acre on these zones, and then cut these back to just 1 or 2 tonnes per acre. The catalyst to design this product was when I purchased this property. This is 10,000 acres inside the tree line, and it has very shallow soils. So instead of having straight line grades that laser gives you, even with multiplane, putting hinges in there, the world's Earth's surface isn't straight line. It is everywhere is either slightly convex or slightly concave. So I had this dream of being able to come up with a program that allowed the design to smooth the surface but not make it into a billiard table. The experience I had on that previous block that I said we levelled, that had the damaged areas, we shifted around and I'm going to talk in, apologise, I'm going to talk in cubic metres a hectare, but it's 2.5 to 1, but it's not the number that's important, it's the relativity. On the whole of my farm, that I've got about 6,000 acres of sugarcane now, I shifted about 400 cubic metres per hectare, average. If I put my whole farm through an OptiSurface design now, I would have shifted about 150. It's a dramatic reduction. And on my farm, with the grades we've got, you can't pick that it hasn't been, you'd think it's been lasered. The changes in the the changes in grade are so subtle that you're flat out picking it. But the other big thing is, whereas my laser design some cuts were over a foot, 1.5 feet, with the OptiSurface design we were limited to about 4 inches. That's what this country here. So I pretty well knew I had a 10,000 acre development there, and I've now got another couple of thousand over there. That was what I had ahead of me for my own, in my own development. So I justified spending money on coming up with the OptiSurface concept and developing the software for my own personal use. There was enough benefit in it for me. But once we designed a product, if we could achieve it, and I didn't know whether we could at that stage, then I wanted to then make use of the product and market it to the world. Initially, I put it to Trimble. When I came up with the concept and I came up with my simple, logical solution, the mathematics, how it would work, I put it to Trimble back in 1998. And Trimble said they were going to develop it. 6 months later, they hadn't done anything. 12 months later, they hadn't done anything, and they just said they had higher priorities. I came back to Australia and put it to Graeme to find me someone who could have the skills to develop the concept into software, and Graeme said, well, he'd like to have a go at it. And about 9 months later, at about 2 o'clock in the morning, Graeme rang, said, yep, I've cracked it. After that, that was where I pretty well finished my contribution. Graeme has just developed the software and put a lot of what I call frills and additional abilities in the program that just make it so much more useful. We use John Deere's, and the Australian pans, we'll say, are called Horwood Bagshaw. They were the ones first to put these tandem walking beams on the back. They're extremely good for trimming, not as rugged and reliable as a Reynolds or the like now, but they're very good for fast work. Okay, I'm going to hand over to Graeme, and I'll contribute a little bit along the way when the opportunity presents.
I'll put this speaker on and hopefully be able to hear a bit better my Australian accent. Before we go on, is there any questions for Dave at this point? No? Okay. I can't see if you're falling asleep, so if you feel a bit drowsy, just put your hand up and ask a silly question. Okay, so I'm just going to go through a bit more, background, I guess, about the concept before we look at some case studies. So, yeah, I guess we focus on surface drainage, solving surface drainage with this product, rather than, I guess, the lasering has traditionally been for irrigation. This solution works, OptiSurface works with irrigation as well, but we see the big market is actually dryland agriculture for quite a bit. So, but it has applications for irrigation. So, how can you improve infield surface drainage? You can cut ditches through a field, which a lot of people do. You can do laser grading. Now you can do optimum surface landforming. You can also put in raised beds to improve the micro drainage. You've got to be careful when you put in raised beds. You can actually create more ponding in your field than without the raised beds, because it restricts, the water flowing sideways across the raised beds. With landforming, you can make sure that the land's always falling in the direction of the raised beds. So it complements, landforming complements raised beds. Make sure that it makes sure they drain to the end of the furrow. Okay, so what is optimum surface landforming? Just so we can nail it down a bit more, it's modifying the field topography by cutting and filling to a predetermined three-dimensional surface, which is optimised to minimise the earthworks while satisfying water management goals. Very similar to laser grading. The difference is that we're using a curved three-dimensional surface, not single plane type designs or multiple plane designs. Terminology: land planing is when you smooth the surface without any design grades. Laser levelling, in my mind, is when you're levelling dead flat to zero grade. Laser grading is when you're lasering to a grade. And optimum surface landforming is this 3D curved surface. 5 signs you'll benefit from OptiSurface. If water pools in your field for more than 24 hours after a rainfall or irrigation event, then you're probably waterlogging your crops. You want to get that water off. Rice is a different story, and won't pretend to know anything about rice. You guys are the expert in it. But we're really talking about other crops here that don't like standing water. Not to say that you can get benefits in rice production from OptiSurface, which we'll discuss a bit later about smoothing levees out and stuff like that. Field operations are delayed because localised spots hold water. That can, even if you've only got 5% of your field holding water, it can delay your planting and spraying and harvesting dates, which can cost you money on that field, more than the waterlogging just in the localised areas to some extent. If you're sick of high earthworks, using lasers. Number 4, if you're sick of scalping too much topsoil with lasers. Number 5, if you're sick of ditching all through your field, reducing productivity, spreading weeds, etc. I guess we advocate that landforming is a better option for improving surface drainage rather than ditching, because of some negative aspects of ditching in terms of machinery, damage to machinery and stuff like that. Okay, just the comparison between laser designs versus OptiSurface type designs. Now these numbers change from field to field, of course, but just to give you an idea of the kind of differences that we see. These numbers also change as your fields get larger. These numbers usually go up because you're trying to, fit a surface to a large curved field or something like that. But typically, for a single plane, if you fit a single plane to a field with a slope, you might end up with 250 to 750 cubic yards per acre. I've seen some designs over the weekend that you guys are shifting a lot more soil than that in places, and you could argue that there's benefits to shifting a lot more soil to get efficient field layouts as well. So yeah, rice is a bit different, but we'll keep going. Multiplane, if you split that same field up into multiple planes, then you might get the earthworks down quite significantly usually, say down to 150 to 375 cubic yards per acre. And then if you do the same design, the same field with OptiSurface, because it allows more flexibility in the slopes, you can get those earthworks right down a lot lower. When you get these earthworks down a lot lower, you open up the landforming market to a lot of area that wasn't feasible to landform before, like dry land, say wheat somewhere that they're not irrigating, but they have drainage problems. You just can't afford to put a laser over the blocks, but you can do landforming. Also, your topography around here, where you've got rolling country that, slightly rolling country, I guess, that you've got levees going everywhere. You can use OptiSurface to smooth that surface out, so you don't see the levees they mightn't be straight like a laser you get from a laser design, but at least you can straighten them out and space them out more for and reduce the number of levees in the field. Okay. So how does OptiSurface dramatically reduce earthworks? Well, instead of fitting a plane of best fit, OptiSurface fits a three-dimensional surface of best fit. So if you've done a laser grading design, you import your topography, you tell the software to calculate the plane of best fit, and it'll come up with a surface. In OptiSurface, it's very similar, except you tell OptiSurface the slopes that you'll accept in the field and a few other parameters, but we'll have a look at that a bit later. A 3D surface is much more flexible to follow the natural topography than a plane, as you can imagine. A lot of fields have concave and convex slopes in them, so you're trying to fit this laser plane through it. It doesn't lend to following natural topography. But OptiSurface, you can make it as flat or as undulating as you want. And it's up to you to decide how much earth you want to shift, basically, to achieve your objectives. Often you don't need single grades for drainage or surface irrigation. Everyone thinks to get efficient furrow irrigation, you need a single grade. It's not true. Slope is not the most important factor in getting a uniform irrigation. And for drainage, definitely not. It's even less. If you're just trying to get water off your field, so there's no ponding, and you definitely don't need a single grade to do that. 5 benefits of OptiSurface compared to laser: lower earthworks, lower cost, less topsoil movement, big driver, less yield impact in those areas. Or if you're topsoil stripping, then you have to, with OptiSurface designs, you have to strip less topsoil effectively. Easier operation. This is more to do with the GPS machine control side of it, not OptiSurface. drains. You get better field layouts, so you can be more flexible on achieving a layout that might be better for machinery productivity, stuff like that. So when will OptiSurface not offer a significant benefit? If you're dead levelling a rice bay, then OptiSurface has no benefit because it's just a single plane, on zero grade. So the machine controls, GPS machine control can offer benefits, but OptiSurface, the concept of curved surfaces isn't going to offer you any benefit at all. If your field has already been laser graded, then putting OptiSurface design over it, it'll do it fine. You'll come up with an OptiSurface design, no problem, but you won't see much, you won't see Earthworks any different to, someone sat there with the laser design program and copied the previous design slides. If you're cutting against the natural grade for some reason, you want to run water into a hill for some reason, because that's the only way you can run it, then OptiSurface will just end up with a design somewhat similar to a laser grade design, because you'll just end up going that minimum grade into the hill. If water's not standing in your field, rather than, I guess this is targeted at the Midwest of the US, where they have a lot of subsurface drainage because they have water infiltrates the soil, hits the I guess runs down the slopes and then pops out as a seep or like a spring, halfway down the slope. That waterlogging from that can only be solved by subsurface drainage, tiling. OptiSurface is all about surface drainage, so making sure the water has nowhere to pool on the surface. Potential areas of application. It's definitely got applications in surface irrigation. But I think the bigger markets are probably heading towards either overhead and drip irrigation. Drip irrigation where you still want good surface drainage, but you definitely don't need single grades to achieve that. And then dry land farming where you've got where you're not irrigating but you have drainage problems. I guess around here you guys are irrigating just about 100% of your land anyway, so that's not applicable. We're kind of looking at the top end of this graph. Okay, I think next on, we go through a case study on a field, just to give you, see how it works. Any questions before we move on?
I've just got a question for how many people do actual multiplane designs on their land rather than one? Okay, there's a few of you there. I'll just throw in where Graeme said there's no real benefit for a laser plane design. Yeah, there is for a multiplane design, because if we put your multiplane design into OptiSurface, it will combine all those sections and make it look like just one big section. And there's a fairly substantial benefit. Where you do a multiplane design, you come to a hinge. It is a straight line and then it goes off. Now it might be subtle, but you will, because of the delay in the hydraulics, you can end up with where the join is, where the hinge is. If you're going that direction, it will leave just a little bit more soil on top of the knob. That isn't really distinguishable. You probably wouldn't notice that even though it's there. But what you will notice is where it changes grade at the bottom. Because when it's going that direction and it changes to go up, it generally will just have a little delay and take a little scoop out of this side. So you end up with a little pool of water just there. So there is a benefit for multiplane design going for OptiSurface.
Okay, thanks. too fast for anyone? Is my weird Australian accent confusing anyone? Not? Yes? I can slow down if you want, or I can speed up. Okay. Yeah, I'll just take you through a case study on a field, one of those fields that you saw on the DAVCO AG farm that we've landformed. It's 92 hectares, about 230 acres. It will grow sugarcane under lateral new or drip. This is the natural topography. It skews the metric units, but that is about, from top to bottom, it's about 12 feet over, it's probably about, it's about half a mile, or a bit over half a mile in that direction, and again in that direction. So natural slope is about 3/10. And yeah, it's generally falling in the direction we're going to run the furrows and sugarcane from there down here. So it's generally falling in the right direction. You'd think that may drain pretty well as it is, and it does drain. But if we went in there and just put drip irrigation into that without doing any landforming, and then you put your beds up, this high, then quite a significant proportion of this field will pond water after rainfall in the furrows, which is what we don't want. So we have to do landforming to make sure it drains. If you fit a plane of best fit, that's what it'll look like through the field. If you look at the cut fill map for that plane of best fit, it is red areas are more than half a foot of cut, purple areas more than half a foot of fill. So the earthworks, the average earthworks are about 405 cubic yards per acre. And maximum cut about 1 foot. At $1.50 a cubic yard, that's about 600 per acre. So OptiSurface, these are the main inputs that you put in OptiSurface. There's other options, but these are the main ones you need to put in. And you don't have to put them all in. This is the main one here if you're just after drainage. So you define your main slope direction, so the direction you're going to run your furrows. If you don't have furrows, you don't have to define it. So you define your main slope direction, we're going to run down this direction. We want a minimum slope of 0.11%, which is just about a tenth. We're going to allow a maximum slope of 0.33%, and then we're going to have, this is a smoothing factor, kind of just smooths the surface out a bit. And then you can do this, you can control the cross slope variability as well. So we're going to go plus and minus a fifth of percent, sorry, a fifth, what's it, no, 5/10 on the cross slope, and then another smoothing factor. And we press calculate on the software, and it goes around and calculates the OptiSurface, the Optimum surface. So you can see it looks very similar to the natural topography, and but it has done a bit of cutting and filling to ensure that we get good drainage on this field. So this is the cut fill map for that OptiSurface design. The legend's the same here. So red's half a foot of cut. We don't even get any, we don't get up to half a foot of fill. Oh yeah, there's a tiny bit there. So the earthworks come down by about 75%. So dramatically reduced earthworks. That's probably, that cost is underestimated because the cost doesn't come directly down because you still have to run over that field a number of times. But yeah, that's about just under a foot of cut there that should be. So we didn't reduce there's a point down here that has to be cut off. But you can see the green area is just about, it's only plus or minus an inch out of grade. So just a light, what we call a trim will cover all the other areas, and then we're just shifting some soil around. Now, if we're worried about topsoil, we might want to strip these red areas off before we cut those areas. You can imagine if we only happen to strip these red areas compared to the red area on the previous cut fill map, we'll be saving a heap of time and money. So that's the previous cut fill map. So you can see the difference in the red areas is dramatic. If we look at a good way to get a better feel for OptiSurface is looking at long sections profiles. So this is a long section down that black line here. So you see the black is the existing topography, and the red is the OptiSurface proposed topography. So you can see there's a little ridge kind of knob in the middle of the field. The OptiSurface design kind of follows the natural topography as close as it can, and then kind of rises up to try and get over it, and then drops back down. We've got these, that was our maximum slopes settings. If we loosen these off, so we have a lower minimum slope and a higher maximum, we can follow that natural topography more closely and then get the earthworks down even further. So you see that's, if we take the slopes down to 0.05, so half a tenth to 10 tenths, you can see it's really closely following the natural topography, just making sure that we get rid of these little areas of good pond water. Earthworks, that's 90 cubic metres a hectare. It's actually about half that for a cubic yard grade, so it's about 45. So we halve the earthworks by loosening our slope inputs. Yep.
What is the 0.05% slope in relation to what we call tenths of a foot?
Yeah, half a tenth.
That's a half a tenth?
Half a tenth, yeah.
Okay.
Yep. Half a tenth. So 1.1% is a tenth.
Okay.
So we generally, half a tenth is as low as we'll go on for trying to get drainage. A tenth, we'll probably prefer a bit steeper than that. For good drainage. Okay, so OptiSurface also has some options for different surface types. One is road drainage. We call it OptiSurface 1D for one directional drainage. So it's road drainage in one direction only. So if you're furrow irrigating and you want the water to flow from one end of the furrow to the other end, then that's OptiSurface 1D. That's the surface type you'd use. If you're say growing soybeans on beds, but you're irrigating with say a lateral move or a centre pivot, you may be happy for the water to drain out either end of the furrow, not out one end, and that's called OptiSurface 2D. So road drainage in two directions. If you've got a ridge in the middle of the field, the water can run out either end. That's OptiSurface 2D. And then OptiSurface 4D, this is where it's four-direction drainage. So you can drain the water can drain in any direction as long as it leaves the field. So that's for things like growing wheat with no, on the flat, or corn on the flat, where we just want to make sure there's no depressions in the field that'll hold water, and the water will just meander its way off. So this is a case study on another field just nearby, the previous one, which we'll look at 2D and 4D analysis. So if we do a 2D design over this field, it's basically there's this little ridge here that naturally there's this little ridge. Naturally there's this little ridge that runs down here that it might be easier to push the water back, to drain the water back this way and have it drain down here rather than trying to fill this area up and make it drain down this irrigating, then you could run your poly pipe down that ridge and then irrigate it both ways up there. Yeah, there's a little knob here, there's some ridges here, so if we, in this case, the water's going to drain down the furrows again, but it's going to drain in this area here back that way. And that's a long section through one of those points. You can see it's rolling both ways. Now, this is an OptiSurface 4D design, so we're growing rice. You could apply this to rice too, actually. But it's where you don't have any furrows or beds to restrict the water flow. So we're just smoothing out the surface here to make sure there's no areas that hold water. There was an area up here that ponded some water, but you can see it smooths out the contours, which in your case can offer a lot of advantages in effectively smoothing out your levees, so you don't have to have a lot of roots in your levees. You can apply OptiSurface as much or as little as you want, just to smooth out your levees so that they're straighter and obviously smoother. And you, yeah. Okay. Yeah, that's just the existing topography beforehand. You just smooth out of it. Okay. Any questions for Jeff? Has a quick talk about how you get this stuff implemented in the field, machine control. Yes.
How about the last slide you had there?
Sorry?
You go back a couple of slides there?
Go back a couple of slides.
Go back a couple of slides.
Okay, how you plan on watering that old field there?
With rice?
That's an exaggeration. It's really pretty flat, correct?
Is it? You say it's really steep?
Hold there.
This one here? Show this one? This hole? This hill?
I think he's just showing how to get the water off by draining any direction. Is that correct?
Yeah.
This is a 4D design. So 4D design, the goal of a 4D design is to get water off. This is more designed for a dryland field or something that's under a center pivot. You're just trying to get water off the field, whatever direction it goes, by moving this little dirt off. So this one you wouldn't necessarily be watering down a furrow or anything else. We use a different design for that. Is that?
Well, I mean, you could run levees on those contours.
Yeah, you could water.
And just water it as you normally water a levee.
I just add that, yeah, there's a 100-to-1 vertical exaggeration here. So it looks like it's a mountain, but no, it's it is significant, 13 feet. But what Graeme was saying, it could even be, you could imagine that for rice. If we took the a block back down, we can do an OptiSurface design and make it the maximum that you are prepared to accept within a bay. Say, just for example, this was one bay. You just tell the OptiSurface design that the maximum point on the field is a certain elevation, and the minimum down is whatever slope. It might only be 6 inches difference from there to there. Imagine 6 inches difference from there to there, just with that sort of different topography within the bay. It means it still drains. At the end, all the water comes out as soon as you let the water out at the lowest point.
Any other questions? Yes?
What degree of slope in those covers?
The elevation, the vertical elevation is
to metre. 31.5 to 32.5.
That's half a metre, so a bit over a foot. So, yeah, for rice you've got a lot of levies in there. In terms of slope, yeah, naturally that's around, well, yeah, it's 3/10. 3/10 is kind of, I think we set the maximum slope on that at 3/10. So, the closest levy spacing you have on 3/10 is, what's that? Sorry?
3/10,
Yeah,
you got a whole bunch of levies,
3/10.
a whole bunch.
Two-
You
two-
can
no,
really,
wait,
you
2/10.
can have them every 100 foot realistically.
Yeah,
If
100
you ran
foot.
your levies on
Yeah.
3/10, you'd have a
Yeah.
levy every 100 foot.
Yeah, yeah, about 100 foot for 3/10. So, but you can smooth it. You can smooth OptiSurface as much or as little as you want. So if you want to shift a lot more soil, you just tighten up the smoothing, or reduce the maximum slope.
Basically,
so
you
you
leave the contour of your ground the same, you're just gonna smooth it out.
Well,
With a 4D design.
no, you can take. Oh, sorry, 4D design. Yeah,
If you wanted to minimize your dough, you're
Yeah.
gonna leave your levees contoured the same, you can smooth them out, flatten your whole field, but still remain at that same natural contour.
basically, yes, smooth your levies out, or you can adjust your maximum slope and your minimum slope to approach a single plane.
Basically, you
Anywhere in
got
between.
scientific hobnobbing running.
Yeah, basically.
It's the way I would put it,
Yeah,
without a lot of guesswork. And
Yeah,
and
exactly.
you're gonna match up, not where you're gonna get
Yeah.
a place and have different elevation.
exactly.
I'll add, I'm a farmer that loves square layouts. There's nothing more efficient